Hi everyone, welcome back to the Bay Delta Schism User Guides. This is Eli Atelovich of the California Department of Water Resources Delta Modeling section. This presentation is the first in our series on meshing and gridding, and we're going to go over general principles for gridding the horizontal mesh for Bay Delta Schism. First, I want to make a few inspirational remarks about why gridding is even important. When we gave our first Bay Delta Schism workshop, attendees were baffled why we would even introduce the topic at all. I think a lot of folks got used to the conception of a model as something that's kind of rigid or fixed and always used in the same form. And that works for applications of Bay Delta Schism where you just want to change a few boundary conditions or gate operations. However, in the studies that we see in practice, it's probably equally common to have to extend the mesh to accommodate restoration or sea level rise. We handle a lot of project-specific questions about details like local velocity or water quality impacts. And those often require increasing resolution or adapting the mesh to a project area. So even if your first application is relatively simple, it's good to be aware of the resources for gridding. So the next question is, how do we do it and what makes for a good mesh? We presently use Aquavio SMS, a proprietary product, to do a lot of our gridding, and we have a number of presentations and videos in this series to talk you through that process. However, the subject of good meshing goes way beyond one tool, and this presentation is going to be a little bit more tool neutral. Each physical term in the flow equations, like advection, viscous effects, and wave propagation, is associated with its own gridding ideals, such as flow alignment, orthogonality, area ratios, etc. Many regions in the Bay Delta also have their own demands. For instance, channel alignment in most of the Delta, resolution of tidal pumping in Frank's tract, and enough cross-stream resolution of geometry to capture variation in velocity and tides across channels. One topic that will come up a lot this session is bathymetric or flow conformity, where you want the mesh to either follow along the contours of the terrain or be aligned with the flow direction. This is an important requirement for gridding, probably more so than the traditional measures of grid quality, although you have to keep a balance between the two. Let's start with an overview of the horizontal grid generation process for Schism. Some of the steps may not even feel that much like gridding. For instance, you need to assemble elevation models and your line work and other visual cues for delineating important spatial features. You need to make your key gridding decisions in what we call a conceptual model. So you'll look for critical contours. You will make decisions about resolution and grid density, and you'll also decide on whether you want quadrilateral or triangular elements in a particular region. You'll generate and polish the mesh in the tool, clip it as necessary to focus on subdomains of interest, and there may be hypothetical versus historical context differences. You incorporate the finished mesh into the preprocessor, and that'll allow you to adjust affected components like the placement of hydraulic structures or boundaries, flow requests, etc. And that will also give you some indicators of mesh quality, and in particular, if you've sort of actually accidentally generated very tiny elements that will hurt model performance. By the way, when I speak of the preprocessor, I'm talking about the Skimpy toolkit that's part of the Bay Delta Schism project and documented elsewhere. Everything starts from bathymetry, and the first question that you're probably going to ask is, where's the bathymetry? So rather than give a hard link here that's going to just be superseded in a couple of months, I want to point out that the location of all of our larger products like bathymetry or atmospheric products is given in the Getting Started page in GitHub. You can write down the URL here, but it's also usually searchable using Bay Delta Schism documentation as the search term. We do a lot of work on bathymetry ourselves. We support a seamless bathymetric DEM or digital elevation model at 2 meters resolution through most of the Delta. There are two versions of that elevation model. One is the released model in all of its details and wiggly glory, and the second one is a set of tiled TIFF files. That's a format that we use for modeling that has light smoothing to get rid of subgrid scale wiggles that tend to cause a kind of a jagged mesh. The smoothing process we use, which is based on a curvature flow algorithm by Melody and Sethian, does not disrupt or dumb down local gradients like so many smoothing algorithms do, and it also tends to be volume preserving. A prioritized list of the DEMs we use to populate our mesh in YAML format is part of the template section of the Bay Delta Schism GitHub page. If you download Bay Delta Schism from GitHub, you can see the DEM names stacked in order. Next, it helps to consider how Schism sees that bathymetry. The shape functions in Schism are linear over triangles and bilinear over quads. For the interior of the channels, this is a pretty accurate representation. In many cases, it's more efficient than piecewise continuous subgrid representations. On the shores, though, the representation is in order less accurate, and there's always a tendency for bias in piecewise linear representations in curved channels. You can see this in the picture with the little cracks that develop near the bed. For any model, you need to know the wetting and drying rules. In Schism, this is a decision that cascades from element to edge to node and back again. The designation is made at the element level, but it makes that decision based on the surrounding nodes. If any nodes are dry, the element is declared as dry. This will disable some velocity backtracking calculations at edges, which has a kind of a flow blocking effect. So it helps to have at least one clear flow path of wetted elements on any channel that's meant to be sort of perennially wet or have flow all of the time. Okay, so let's look at some cases and possible pathologies. In the top left case, we have gridded only at the shores, at the two red dots. Our preprocessor will adjust this a little bit, but if you gave it to Schism just as is, then what would happen is it would just see shallow on the left and shallow on the right, and it wouldn't even notice that there's a channel in between the two. So you'd have no conveyance in that channel. In the top right picture, the left side of the channel is flowing, but the right side is clogged, and it's probably a bit under-resolved. In the bottom left channel, the channel is a bit clogged, and also it isn't resolved terribly well. There's this big crack here in between the piecewise linear representation and the more curved channel. And the bottom right, the grid resolves the feet of the levees, and it's dry, but the harm is minimal because it's kind of restricted to the levee slopes. We can layer in some fixes. In the top left, I moved the elements down so that they're at kind of an average depth for the whole cross section. So now it will have some conveyance. Obviously, it's a 1D representation, but Schism works pretty well in that capacity too. And then on the right, I've added a couple of extra nodes that mean that the sort of switching off that happens as we traverse the intertidal zone won't have as much of an effect on momentum. On the bottom left, we can add an extra node, and now we're following the contours of the bed much better. On the bottom right, we have a grid that's been converted to a more well-resolved channel. Not only is the intertidal transition discretized, the extra resolution near the shores is often pretty useful because there are usually sharp velocity gradients developing right near the shore. Under-resolved grids typically depict the velocity gradient in more of a molasses or parabolic kind of a shape. That the velocity profile isn't quite right, even though the total amount of flow is acceptable. So this is probably what you would want to do if you were focusing on the area, and it's kind of a transition as gridding goes on with Bay Delta Schism. There's been a kind of a resolution creep towards this type of representation. So we've established that the always wet line should be gridded because of its importance in the wetting and dry rules. And in the tool-specific videos, we're going to talk about how to snap nodes to contours. There are a few other contours to be aware of. So you should always be aware of algorithm switches and how you might want to grid it's kind of along the contours that represent those switches. So one example is HTVD, which is a depth trigger for using a higher resolution transport scheme. Usually that's 5 meters in the model. And we have some depths in our friction formulas. So again, it's better if the conformity to those contours is in the along stream direction, so that the water doesn't, when it's going along the main flow path, it doesn't develop a numerical boundary layer from suddenly hitting this new treatment. I put a few notes about useful contours in the bottom right of this slide. It's impossible to specify an always wet elevation that works through the entire domain. About 0.25 meters NAVD works well towards the ocean side, and that kind of creeps up towards 0.6 in the South Delta. Always good to play it safe, particularly if you're meshing a little bit rough or quickly. It is important that you not create blockages. So let's see how all this advice about contours comes together in an applied example with messy features such as shoreline undulation and intertidal areas that don't line up very well with the main channel. The example that we're looking at is from Old River. First, I'll get rid of the background map so that we can focus in on the contours. The deepest part of the channel is about -4 NAVD. It's kind of in the top left up here. The lowest tides reach about 0.5 meters NAVD, and 0.45 is probably a safer or more conservative always wet elevation. Notice that the 0.55 meter contour undulates on both sides of the grid. So that is this one here, the sort of purple line, and it doesn't track the center channel very well. The center channel here is very clean. So the way I usually handle this is to grid from the center out, starting with the deeper section that's clean. In this example, I put 4 elements in the deep part of the channel. Next, I grid up the slope to the always wet contour, which is about 0.45 meters. There's a little wiggle to go with that choice, but you can see that we've got a clean grid on the inside, and then we've captured that undulation in a simple way. And then we start capturing the intertidal area and extra storage area on the sides. So that's probably a good introduction to bathymetry. So now let's talk about gridding conceptual plans and how you integrate choices about quads and triangles and bathymetry all into one plan. Quads and triangles, first of all, we use quads a lot of the time when we can, certainly in channels and certainly when flow alignment is a focal issue. It's also worth pointing out that quads are more computationally efficient. We tend to use triangles in embayments, open water, side storage areas, places where its advantages are that it can conform to a general geometry really well. It's fine to use triangles in areas where we don't have a good concept of flow alignment, but again, it's a little bit less efficient. Side storage, again, floodplains, and also one thing to point out is, and it's shown kind of in the bottom right of this slide, is that we always try to avoid abrupt streamwise transitions in any part of the algorithm, but also between quadrilaterals and triangles. A numerical boundary layer will develop here, particularly if it's in an area with baroclinic exchange, like I ran into it once with a section of Carquinez Straits. As far as resolution goes, the distributed version of Schism is intended to be infrastructure. We want to get the system-wide performance right, and our hope is to resolve the main processes leading to circulation scale exchange flows and transport, including the balance between horizontal and vertical processes. The limiters for modeling in the delta tend to be differential advection and jet in channels and the jet sink exchange at Frank's track. We also find a lot of resolution sensitivity at the entrance and exit of Sassoon Bay, where you have the connection either to Carquinez Straits on the west side or the main channel of Sacramento on the east side. Out of the box, the grid cannot be construed as a detailed model of small channels everywhere in every sub-region. And in a sense, that's why we're here today, because you might have to provide that extra bit. Despite the caveat, Bay-Delta schism is considerably more resolved than any other multidimensional model in the Bay-Delta system. So, well, that still doesn't answer the question, how finely should I mesh the channel? And I realize that no one likes hazy advice, like it depends on the physics. So while it absolutely does depend on the physics, and you need to know what physics control your problem, I want to give a few starter guidelines that I think work well for channels in the, let's say, central delta, 20 to 300 meter wide. Sometimes you see similar sort of internal channels in embayments. So start by choosing the cross stream direction and consider the velocities, how velocities will change between the shores, and in any interior subchannels such as a deep thaw wag or a ship channel. We usually use quads in the channels, and a good rule on shape is to strive for no more than a 2-to-1 aspect ratio streamwise to cross stream. So you start with the cross stream and then you get the streamwise level. We have some elements that are more skewed in our existing mesh, so you may see that we haven't followed our own advice sometimes, but we like to gradually improve. And as you'll see in some of our hands-on videos, in places like junctions, you really don't want to have a lot of anisotropy at all, so you want to get more closer to a square, less like a rectangle. Okay, back to the cross-stream direction. For a really low-resolution case, less than 20 meter wide, you can grid schism one element wide. As part of we saw an example of that already, and the preprocessor will fix that up. So some of the defects that I showed with elevation won't actually manifest. It will give you a balanced sort of average depth. If you go 3 to 4 elements wide, you can maybe capture the essence of the geometry. You get the feet of levees, let's say. And a more medium resolution approach would be to use 3 to 4 elements wide just on the smoother interior portion of the main channel, tacking on 1 to 2 elements off the slopes or to capture some of the intertidal zone or side areas. A fully resolved case would grid the main channel 6 to elements wide per side, maybe more if there's an interior channel. Again, you would want to mesh at least 2 elements on either side in the levee or shore areas, particularly if there's vegetation or sharp gradients. And generally, you want to focus resolution towards the sides of channels at the transitions between those side areas and the main channel. No guarantees, but I hope this helps. We'll try to post a few coordinates where we think the principles are applied well. The next issue is something that I call numerical groundwater, which is a kind of quirk of the finite element method used in the solver. Schism can produce water running underground or through levees if you have just one dry node, or you could flip this and say one wet node, and particularly if the bed is undulating. So you're going to want to mesh elements so that you put 2 nodes and kind of resolve the levee crest or thaw wag. Eventually, when you populate the grid, you can also use some of our depth enforcement techniques using polylines or polygons to make sure that this is the case and that you've got the levee reinforced. If you're working with SMS, our current tool of choice, I'd like to point out that we have another half dozen additional practical videos on grid setup using SMS. These include an introduction, recipes for channels, description of tools for controlling resolution, one on debugging errors, and a description of how to build the official mesh using the same workflow that we do. Also one on cutting and stitching maps on meshes is in progress right now for collaborative work. Keep practicing. As with anything else, meshing gets a lot easier and a lot faster as you go along. And with that, I hope you enjoy your meshing journey, and thanks for joining.